Hello and welcome. This is the course on stochastic processes and the theory of queues. In this lecture, we will look at a generalized version of the renewal process. It is called as the regenerative process. Then we will look at a particular case of regenerative process that is quite often encountered in real world scenarios. It is called as the alternating or on-off renewal process. So in the case of renewal process, we saw that there are time points at which the process forgets history and renews itself. If the time difference between two such renewals, those times, if they are all IIDs and exponentially distributed, then it is a Poisson process. If it has a general distribution, we call it as the renewal process. But we saw that the successive renewal durations have IID random variables. But it may so happen that there are different states in which the process can be present. In a particular state, when it enters, then the amount of the time it spends in that state and to the different states it can go again in the time days it spends in those states and so on can be varying. But it may so happen that a process after spending some time in other states may come back to a particular state, in which case its behavior is as if it was in the initial time when it started off in that state. So we will say that the process has probabilistically renewed itself or regenerates itself. So those are called as the regenerative process. So a stochastic process x of t greater than or equal to 0 with state space, discrete state space 0, 1, 2, having a property that there exists certain time, say t1, such that after that time t1, it probabilistically restarts itself. Whatever predictions that you may make at the initial time, those predictions or same predictions holds good at that time t1. So we say that it is stochastically or probabilistically identical at the initial time and at the time t1. Then existence of such a time t1 for the case of the regenerative process guarantees that there will exist another time t2 when you consider t1 as the initial time, such that t2 is a time in which it probabilistically regenerates, and so on. There will be another time t3 and so on. So there will be time points t1, t2, t3 where it probabilistically regenerates or identical. Depending upon what state you take as the initial state, you will have the time at which it comes back to that initial state will change. But these processes have the property that based on what state you take as the initial state, whenever it returns back to that state, it probabilistically regenerates itself. So these points t1, t2 constitutes the point at which it regenerates, and it is the time at which we can view it that at those points it renews itself. Okay. So the difference is that the renewal process is a regenerative process, but not necessarily the other ways. Here t1 represents the time at which the first renewal takes place and so on. If you have a recurrent Markov chain, that is, has no absorbing states, where with a probability 1, a process having started at a given state will come back to that same state. If t1 represents the first time for it to return back to that state, transition back to the initial state, then the process is a regenerative process. So how do we model it? So we are, in general, in a case of the regenerative process, we are interested in finding the long time run proportions over a long period of time, certain averages that the regenerative process spends in a particular state J. So there can be many states in which the process can be there. So in a long run, what fraction of the time it spends in the state J for each state of its finite state space. So to obtain this quantity, we have to imagine that, let us say we earn a reward at a rate of 1 per unit time whenever it is in the state J, and 0 when it is not in the state J. Then we can define a indicator random variable to indicate when rewards are being obtained. So I of s represents the rate at which it earns the reward. So I of s is equal to 1 if x of s, the state in which the process is present, is J, and 0 if x of s is not equal to J. Then over a time t, 0 to t I of s ds indicates the total reward obtained in the duration 0 to t. Then the average reward per unit time, or the rate at which rewards are obtained, is nothing but take a long duration, find the expected reward obtained during the time t divided by the time t. If you take, you know that this is a regenerative process, so it regenerates at the time t1 starting from initial time. So even if you let the time interval to be t1, it need not be infinite, then this average will be equal to the long run average. So the average reward obtained per unit time is just expected reward by the time t1, where t1 is the time at which it regenerates, divided by the expected duration of regeneration. Then we will look at one particular example of the regenerative process, which is very often encountered. That is called as the alternating renewal process. Assume that you have a process which can be in two given state, such that it spends some amount of time in the first state and then goes to the second state, such that after spending that amount of time in the second state, it comes back to the first state, and so on. So if you look at a Markov chain, there are two states, and there is a transition, CTMC, transition from one state to another state and another state back to this state in a circular manner. So we will call these states as on and off state. Initially it is in the on state and it remains on for a time duration, say Z1, where Z1 is a random variable. Then it goes to the off state. Again it remains in the off state for a random amount of duration, which we will call it as Y1. After that it comes back to the on state, but now the time spent in the on state during its second visit is a random variable Z2. But Z1 and Z2 are independent of each other, but have identical distribution. So Z1, Z2, Z3 are the successive time it spends in the on state whenever it visits the on state. Similarly, whenever it visits the off state, Y1, Y2, Y3 are the time spent in the off states. Y1, Y2, Y3 are IID random variables, have the same distribution. Similarly, Z1, Z2 are all IID random variables. But we may assume that the duration of the off state is dependent upon the duration of the on state. So This is something that we allow, which means that if you look at the regenerative points, whenever it gets into the on state, it regenerates or renews itself. But the next regenerating does not takes place when it gets into the off state, because the off state duration is a function of the on state duration. So when it comes back to the on state, it regenerates. Now let's try to find the proportion of the time it spends in the on state and the proportion of the time it spends in the off state. So because zi's are IID random variables, we can find a common expectation for z's. We will call it as E of z. Let E of z is equal to E of zn. Similarly, E of y is the common expected value of y's, E of y's. So these are what are called as the mean lengths of the on and off periods. So we are concerned with the probability that at a random instant, if you look at the process, it will be found to be in the on state. That is P on. Or it is the long-term proportion of the time the process spends in the on state. So we will introduce a notion xn, which is the duration of the nth regeneration cycle, which is the sum of the nth on duration plus off duration. Okay. So at the time x1, the process starts over again. The process renews itself. After one complete cycle consisting of an on and off duration, it again renews itself. So the probability of on, it is can be found in the on state, is E of z divided by E of z plus E of y. That is the expected on duration divided by the expected renewal cycle duration, which is the expected on plus expected off. So we can find it as expected on divided by expected on plus expected off. Probability that the system will be found to be in the off state is 1 minus the probability it is found in the on state. So it is just 1 minus of this, which can also be written as expectation of the off duration divided by expected on plus expected off. One example of where on-off regenerative process is encountered is, we often assume a communication channel to be in two possible states, one in good state, another bad state. So normally the communication channel will be transmitting bits at one specified bit error rate, which occurs due to the normal ambient conditions. But sometimes due to some voltage fluctuations or unforeseen reason or bad channel condition and so on, the BER may increase and we say this state to be bad. Then again the duration for that bad duration, which is triggered by some external phenomenon, it's a random duration, it will persist for some time and then it will come back to the normal state of the channel. So we say we can model the channel to be in two possible states, on and off state or good and bad state, and we can find the expected time it will be in good state. The process will be found in the good state as expected on good state duration divided by the renewal cycle duration, which is expectation of good state duration plus expectation of bad state duration. Similarly, a production process can be modeled as an on-off or alternating renewal process. If you use a machine for a production purpose, when the machine is working, we say the machine is in the on state and it works for a random amount of time and then breaks down. Once it breaks down, the machine is put into repair and it cannot produce any goods, and it takes a random amount of time for the repair to occur. So the initial time for which the machine is in the production state, we will call it as Z1. When it first breaks down, the first duration it takes to repair the machine, we will call it as Y1. Once the repair is completed, we assume that the machine is as new as the original one, and it will again be put into use or production, and the next production cycle starts until it breaks down again, and that duration we will call it as Z2. The next repair duration we will call it as Y2. So the durations will be Z1, Y1, Z2, Y2, Z3, Y3 and so on. So here the on and off state alternates, and we can find the fraction of the time the machine will be in the production state easily. An interesting example comes in the domain of insurance. Usually the insurance companies has a policy for its subscribers or policy holders, a policy for the policy holders of how to charge the premiums, insurance premiums for health or life or for some goods like car and so on. So what happens is that it has two possible premium rates. One we will call it as R1, another R0. When a new policy is started by a policy holder, initially the subscriber is charged at a rate of R1 per unit time. The time may be a year because annually the insurance may be renewed. So the initial rate is R1. When the policy holder who is paying at the rate R1 has not made any claim for certain number of years, then as a reward or a bonus to the policy holder, it reduces the premium to a value which we will call it as R0. Different insurance companies have different kinds of rewards to the customer who they are called as the no claim reward, because when there is no claim it benefits the company because they have been getting premium and the customer is not making any claim. So therefore to encourage the customer to avoid making claims, sometimes for small cases the policyholder may not even claim, okay, because this policy which we will see penalizes whenever a claim is being made. So for a duration of S years, if no claim is being made, the premium is brought down from R1 to R0, and it will remain in R0 until a claim is made. The moment a claim is made, the premium is brought to the original value R1. So this is how the premium alternates between two rates R0 and R1. To understand what is the average rate at which a policy holder pays at a rate R0 or R1, we can do as follows. First, we need to model the process governing the claims that are being made. Claims are made because of certain reasons. For example, if it is a car insurance, whenever there is an accident, then a claim is made. In the case of mediclaim, whenever there is an illness or a sickness condition, a claim is made. So those are all random events that occur. We will assume that the duration between two such events that leads to a claim or is a Poisson process, and the duration between two such claims is exponentially distributed. Okay. So we are interested in PI, the proportion of the time the policy holder pays at a rate Ri, for I is equal to 0 or 1, that is at the rate R0 or R1. Similarly, the long-term average amount paid by the customer. So the x, the time interval between two claims, okay, is a random variable, and we will assume that to be has an exponential distribution. So we say the cycle starts whenever the rate becomes R1, which is the initial rate at which the policy is started. So when a policy is started at a rate R1, it's the first point at which the process starts. Okay. Then as we proceed at an arbitrary time, we cannot predict future because we won't know how long it has spent with that rate R1, because after spending S years, the rate will change, and again then depending upon when an event occurs and a claim is made, the rate will change. So because the point at which the process regenerates at the point at which a claim is made, and therefore the rate becomes R1. Okay. To do that one, we will first compute the expected duration of the on time of a cycle. We will say an on time is a one where the rate is R1. We can see that it is the minimum of x, which is the duration between two claim, and s. Suppose x, the duration between two claim, exceeds s, then what happens is that is the rate which has been originally R1 becomes R0 at the time point of s. So the duration of the on time, that is the time at which the rate is R1, will become s when there has been no claim till s. On the other hand, if a claim is made at a duration x which is less than s, then immediately the process regenerates. Again we reset the counter. If you say we have a counter which keeps looking for the elapsed duration between two claims and check whether it has exceeded s or not, we reset the counter and again look for a duration of s before switching the rate back to R0. Okay. Yeah. So it is the duration of the on time is a minimum of x or s. Note that when x is the case at which the claim occurs, which is less than s, the duration of the off cycle is 0. That is, in one cycle, that is between two claims, the on duration itself is the whole cycle duration, because he has been paying at a rate R1, claim is made at a time x less than s, the policyholder continues to pay at a rate R1, so the R0 duration is 0. Okay. So what is the expected on time of a cycle? To find out this, if x is capital X denoted as small x is less than s, then what is the expectation? We know that x is exponentially distributed with a parameter lambda. Therefore, it is 0 to s x lambda e power of minus lambda x dx. That is, we are integrating over the probability density function of an exponential distribution only from 0 to s. In case this x, the duration between two claims, exceeds s, then for the remaining time it is s. This happens when x is greater than s. Okay. Now this duration is the off time duration when the payment is at the rate R0. Because it is an exponentially distributed, irrespective of the fact that it has already spent s, the remaining time will also be exponential with the same rate lambda. So we have to find the remaining rate, okay, of x is the CCDF of x evaluated at s, which is e power of minus lambda s. So at a remaining at a rate it will be s e power of minus lambda s. Okay. So we can find out this is 1 over lambda 1 minus e power of minus lambda s. Then what is the duration between two regenerative points? It is the duration between two claims, because the claims occur, or the events that lead to claim occurs based on a Poisson process with a rate lambda. Inter-event times are exponentially distributed with a rate lambda. E of x is 1 over lambda. So the cycle duration is just 1 over lambda. So P1, the probability that the premium is at the rate R1 is expected on time divided by expected on time plus expected off time. But on plus off time is the total cycle duration, which is E of x. So it is 1 by lambda e power of minus 1 minus e power of minus lambda x divided by this 1 over lambda. So 1 over lambda get cancelled, we get 1 minus e power of minus lambda x. So P naught is just 1 minus P1, which is e power of minus lambda s. So in a long run, the average rate at which premiums are being paid, if you want to find, it is the expectation of the rate at which payments are being done over a long time. But we have found out that we don't need to do an averaging for a regenerative process over a long time. If you do it averaging over a regenerative cycle, that is enough, because it probabilistically renews. So that is equal to R0 into P0 plus R1 into P1. So plugging in the values, so R1 into 1 minus e power of minus lambda s plus R0 into this quantity, and rewriting, we get the value, it is R1 minus R0 into e power of minus lambda s. So this concludes our discussion on the alternating renewal process. Thank you.